Okay, so thank you all very much for coming out here to listen to me babble about black holes and something about the microscopic structure of space-time, what space-time really is at the end of the day. There are a number of other string theorists in the audience, so if you're one of them, please raise your hand. These people can also answer questions for you after my talk if I say things that are extremely confusing. I want to present, after that introduction, I'm not sure I can live up to it, but I'm trying to present some very cool science. The questions I want to address are questions that are really asked very close to where we are now. The beginning of science was our human forebears on the savannah, and I'm sure that after a successful hunt one evening, they looked at the sky and they pondered the big questions. So what are the big questions? The big questions are, how did the universe begin? Why is the world, the laws of physics in other words, the way they are? Could they have been some other way? And in modern parlance, what our early human forebears were after was some explanation, some fundamental explanation for space, for time, and for matter. So these are the questions that in this generation we have the privilege to attempt to answer. So I want to emphasize the kind of things I'll be telling you about is really a labor of generations. It's not one person, the solitary genius who comes up with everything. It's a process, and everything that I'm going to say is provisional. That's the nature of science. The canonical theories we have change with time. So it's really an honor to be able to answer questions as deep as these, at least in part, and slowly make progress towards a final answer perhaps someday. So how do we do theoretical physics? I'm a theoretical physicist. I live on coffee, basically. Some alcohol also helps occasionally for some of the wild ideas. The basic philosophy is that we try to take our theories, the theories we understand, and try to test them at the limits of our understanding. In this way, we refine what a theory is, and sometimes we stumble upon a new theory that better explains, better captures the nature of reality, a physical description of what's going on in nature. So we interrogate the theory at its limits, we test it against other theories sometimes, and we try to resolve any tensions we may encounter. So a very famous example of this was the development of special relativity. So Einstein proposed a thought experiment. Suppose you're riding your bicycle, and suppose you turn on the headlamp on your bicycle. The light from the headlamp propagates at the speed of light. Now, suppose you bicycle faster than the speed of light. What do you see? According to Galileo, the velocities should add. The velocity of light should add with the velocity of your bicycle. Now, James Clerk Maxwell, a Scottish physicist in the 19th century, developed the theory of electromagnetism. According to the theory of electromagnetism, the speed of light is a property of the medium in which the light is moving. So in Cleveland, of all places, in the 1880s, Michelson and Morley performed a famous experiment. They tried to measure the speed of light in the direction of the Earth's rotation, the direction opposite to the Earth's rotation. When they performed this experiment, they found the speed of light was the same, whether they measured it with the Earth's rotation or against the Earth's rotation. Einstein provided an explanation for this fact. So, according to Einstein's theory of special relativity, every observer measures the exact same speed of light. The universe has a speed limit. Now, we know that in Johannesburg, speed limits are optional. This one is not. This is one of the laws of the universe. So we're stuck with the speed limit. The nature is less accepting than Johannesburg's cops. We're stuck with moving at less than the speed of light. So what we've done is we've tested the theory of electromagnetism against the theory of classical mechanics. We found there was a tension. This tension was resolved in favor of a new theory, special relativity, which imposes a speed limit on light. Now, according to special relativity, there is a light cone. So the future light cone is all the points in the universe to which we can send a light signal. This is the only part of the universe which we can influence, because it's the only part of the universe that we can communicate with. Anything outside of our forward light cone is a part of the universe to which we can't send a light signal, because it would require propagating faster than the speed of light to get there, and that's disallowed by Einstein's theory. Similarly, there's a past light cone. Only events in the past light cone can influence physics where we are now. So that's the consequence of the special theory of relativity. So we've seen, by testing these two theories against each other, we've been able to develop an interesting new theory. Now let's continue. So Newton, in the 17th century, had a remarkable insight that the force of gravity, which explains how things fall on Earth, is the same force of gravity that sustains the motion of planets around the sun and the moons around the Earth and so on. So it's the same force of gravity. And in Newtonian mechanics, this force of gravity explains how things fall and how things move in celestial mechanics. So suppose we take this Newtonian theory of gravity and compete it with special relativity and see what happens. If we do this, we get the general theory of relativity. Einstein did this in 1915, so the theory is slightly more than 100 years old. So the way Einstein developed general relativity is he proposed another thought experiment. He was very, very good at proposing thought experiments to test theories at their limits. So this thought experiment is suppose the sun suddenly were to disappear. The sun disappeared, light from where the sun was would only reach us 8 minutes and 20 seconds later. So the sun suddenly vanished, we wouldn't know that it had vanished for 8 minutes and 20 seconds. According to Newton, every mass in the universe immediately influences every other mass in the universe. So Newton's gravity, if the sun suddenly disappeared, we'd go flying off our orbit. Our orbit's nearly circular around the sun. If the sun suddenly disappeared, we'd go flying off the merry-go-round, basically, in a straight line. So Einstein asked, what happens if the sun suddenly disappeared? According to his theory of special relativity, signals can only propagate as fast as the speed of light. So Einstein resolved the tension between Newton's theory and special relativity in favor of special relativity. As a result, he found that acceleration is the same thing as gravity. The presence of mass, for example, a very big mass like the sun, curves and deforms space-time. Because of the deformation of space-time, the space-time curves, and we move in this curved geometry. Our linear motion, the straight line motion in this curved geometry, is the orbit of the Earth around the sun. So this force of gravity is a consequence of the geometry of space-time. That's the deep conclusion of the general theory of relativity. This theory has been verified from the scales of microns in very detailed experiments involving pendula, up to the observable universe, cosmic scales. It's one of the best tested theories in the history of science because it's been verified from the really, really tiny to the really, really big. It's a very, very successful theory. So we can as well construct other theories by looking at what happens when we test them at various limits. So for example, if we take classical mechanics, we import the idea of waves from electromagnetism, and we include thermodynamics, the behavior of a large number of degrees of freedom, we obtain a theory called quantum mechanics. If we take quantum mechanics and test it against special relativity, we arrive at a new theory called quantum field theory. So let me tell you a few things about quantum field theory. So a field has a value at every point in space-time. A field on the Earth, for example, a classical field, might be the temperature. Every point on the Earth has a particular temperature. Similarly, atmospheric pressure. There's another field that has values everywhere on the Earth. A quantum field, similarly, has values everywhere in space-time, not just the Earth. Particles we see in nature are local excitations of these fields. So there's an electron field that permeates all of space-time. A local excitation of this electron field is the particle, the electron. A local excitation of the photon field is light. So everything we see in nature, all the fundamental particles, are excitations of their corresponding fields. To define a quantum field theory, we need to specify the fields in the theory and how they interact. We can draw cartoon pictures that show these interactions. So let time be running vertically, and suppose there was an electron which is passing nearby another electron. They communicate by exchanging the photon. The photon is the quanta of electromagnetism. In exchanging these photons, one electron recoils. The other electron gets a kick when it absorbs this photon. As a result, two electrons move apart, like charges repel. This is a quantum mechanical, quantum field theoretic version of that simple observation. Similarly, we can take the antiparticle to the electron, which is another excitation of the electron field. This antiparticle is called a positron. Suppose a positron collides with an electron. They annihilate, they form a photon. Eventually, this photon, after propagating for a while, can again break up into an electron and a positron. This preserves the charge, of course. So these electrons and positrons, they interact by exchanging these photons. We can draw cartoon pictures. They're called Feynman diagrams. And there is a recipe for evaluating a Feynman diagram. So every quantum field theory textbook is a cookbook for how to evaluate these diagrams. And in doing this, we can determine cross-sections for various processes in nature. For example, electron scattering of electrons. So we can go further, and we've noticed electromagnetism is described as a fundamental force by this quantum field theory, called QED, in fact, quantum electrodynamics. In fact, all the fundamental forces of nature, electromagnetism, the weak nuclear force, which explains radioactivity, the strong nuclear force, which explains how protons and neutrons are bound together, and the Higgs effect, which endows particles with mass, all of these can be explained in a quantum field theory called the Standard Model. Now, the Standard Model is an extremely prosaic name for the best tested theory in the history of science. You do a calculation of the fine structure constant alpha, and you make a measurement of the fine structure constant alpha. They agree to 13 decimal places. This is a very, very good theory. So we've seen the quantum field theory provides a very good description of the forces in nature. We've noticed that gravity acts like a force. Gravity is the response to the curvature of space-time. We experience this as a force between things with mass. Things that have mass coupled to geometry, and we can see what happens as we treat this interaction in terms of quantum field theory. So suppose you've got two masses that are just traveling along, and they exchange a fundamental force carrier, the graviton, just like the electrons exchange a fundamental force carrier, the photon. Does the fact that these masses exchange this graviton mean that the masses get tethered together and are attracted? Well, it turns out that if you evaluate this particular Feynman diagram, you get a finite answer. However, if you evaluate all the possible Feynman diagrams, one graviton is being exchanged, two gravitons being exchanged, three gravitons being exchanged, and so on. And you sum all of these, the answer you get is infinity. The theory doesn't make sense. So if you think about gravity in the language of quantum field theory, you find that the theory is contradictory. We need to resolve this contradiction somehow. So what went wrong in the simple analysis of gravity as a quantum field theory? Well, general relativity explains that the dynamical response of geometry in the presence of matter or energy is to curve, and conversely, the dynamical response of matter to the curvature of space-time is to move in the appropriate way. In a quantum universe, however, things fluctuate due to what's called the uncertainty principle. You can't know the precise position and the precise velocities of momenta of a particle to arbitrary precision. There's this parameter h bar which sets the uncertainty in our measurements of position and momentum. So because if we're treating geometry as a quantum field theory, things are fluctuating at the quantum level, one of the central assumptions of general relativity, everything is smooth, can be described by geometry, that breaks down. So quantum field theory by itself fails to be an explanation of the force of gravity. We need to do better. Quantum field theory is essentially the state of the art. So how do we do better than quantum field theory? Well, this is an opportunity to learn something new, a new physical theory of the universe. We call it quantum gravity. It merges general relativity and quantum field theory in a coherent way. We don't actually know what quantum gravity really is. So the hope and the reason I investigate things like black holes and cosmology is to better understand what quantum gravity is. So a way to organize the things I've been talking about so far is in terms of what's called Bronstein's cube. We've seen that there are three different parameters we've considered. One is the Newton constant, which explains how masses attract, the strength of gravity, in other words. Another is the speed of light. Because the speed of light is finite, it sets a limit for information exchange. How fast can you transmit information from one point to another in space-time? The third parameter, h bar, sets the scale for quantum mechanics. It sets the scale for this uncertainty principle. If you combine these parameters, G Newton, h bar, and c, you can form a length. This length is very, very tiny. It's 10 to the minus 35 meters. It's unimaginably tiny. But that's the scale in which quantum gravity effects definitely manifest. Now, I showed you this family tree of theories, how we compete theories against each other and form new theories. We can populate the vertices of the cube with these various theories. So for example, special relativity is this theory that just turns on the speed of light. General relativity turns on gravity and the speed of light. Quantum mechanics turns on h bar, and quantum field theory turns on h bar and the speed of light. This mysterious thing that we're after, this thing with a question mark, this quantum gravity, turns on everything. There's h bar, there's c, and there's G Newton. We want to come up with a coherent theory that has all of these properties. It has gravity, has quantum mechanics, has special relativity embedded into its framework in an intrinsic sort of way. Now, this picture is also very good because it lets us emphasize a point. Einstein never said Newton was wrong. What Einstein said was Newton's theory is valid within a certain regime of validity. Beyond that regime, you need something new. So if you take the limit of general relativity, in which velocities are small and gravity is weak, Newtonian gravity is a very, very good approximation of the physics. The universe is certainly quantum, but you don't need quantum mechanics to understand the motion of a football. It doesn't really enter into the game. These theories are all connected, but there are limits in which one theory gives another theory. As well, we've seen that there are various slogans we can associate to these theories. So for example, in quantum field theory, fields interact via these gauge interactions, these gauge forces, and particles are excitations of these quantum fields. Similarly, in general relativity, we see that energy couples to geometry, and space-time is not just an arena where things happen. Space-time is intrinsically dynamical. So we want to understand what slogans of this form we can associate to this mysterious thing called quantum gravity. So the reason why black holes enter into the game is they provide a laboratory in which quantum mechanics is operative, in which gravity is operative. So in this way, by studying black holes, we can try to understand this quantum gravity, this theory that is rather mysterious right now. Okay, so what's a black hole? Well, suppose we were doing something like launching a rocket, an Apollo rocket from the Earth to the moon. In order to leave the Earth's gravity, this rocket needs to be traveling at a minimum velocity. It's called the escape velocity. If you plug in the mass of the Earth and the radius of the Earth, you find the escape velocity is 11.2 kilometers per second. This is derived by looking at the potential energy of the rocket and the kinetic energy of the rocket. So in order to leave the Earth's gravity, in order for the rocket to launch and not come back to the Earth, it needs to be traveling at this minimum speed. Now, we just said there was a speed limit in nature, the speed of light. Suppose there was an object that was so massive that even light couldn't escape it. That's a black hole. So this idea that an object could be so massive that you couldn't see it because light can't escape it was first proposed by the English astronomer John Mitchell and the French mathematician Pierre-Simon de Laplace in the late 18th century. The term black hole was actually coined by a journalist, Anne Ewing, in 1964. John Wheeler, who was the founder of the American School of Gravity, he's the guy who popularized the term, and that's where black holes entered into the popular consciousness. Since then, we've seen that black holes were essentially ubiquitous in literature, and we're trying to understand this beautiful structure. So this equation up there is an equation suitable for framing, once you understand it. So the left-hand side, r mu nu minus 1/2 g mu nu r plus lambda g mu nu, is just about geometry. G mu nu is basically how you measure distances on a curved geometry. The other quantities, r's and so on, they're derived from G mu nu. So once you learn how to measure distances on a curved geometry, you get the left-hand side of Einstein's equation. The right-hand side of Einstein's equation is basically what the matter is doing. So the left-hand side, the geometry, tells the matter how to move. The right-hand side, the matter, tells the geometry how to curve. This is a very beautiful mathematical structure that Einstein proposed in 1915. As I said, it's one of the most well-tested theories in science. This is what we call, in the parlance, a second-order nonlinear partial differential equation. It's notoriously difficult to solve. The best way anyone really has for solving these things is to guess the solution and verify that it works. There's no systematic approach generically for solving these things. So Einstein initially believed that this equation could only be solved in an approximation scheme. The only solution he had in 1915 was empty flat space. In 1916, 1 year later, Karl Schwarzschild solved this equation. He basically looked for the most symmetric solution possible, and the solution he found was the black hole. So the black hole has an event horizon. The event horizon is just the surface at which the escape velocity is the speed of light. So once you cross the event horizon, according to Einstein, you can't ever get out again. As well, deep in the heart of the black hole, there's a singularity. The singularity is a place in the space-time where the curvatures become infinite. Again, the notion that space-time is smooth stops making sense at the singularity. So the hope is that quantum gravity, whatever it is, can make sense of these pathologies in Einstein's theory where general relativity seems to fail. We'd like to understand this a little better as well. So black holes, as I said, have entered the popular consciousness. This is still from the Disney movie The Black Hole. We see that Starship Enterprise is escaping from a black hole in one of the Star Trek movies. We see as well the recent movie Interstellar, where there were a lot of black holes. So black holes are in science fiction, and they're also in science fact. So here's a simulation of a star rather like the Earth, rather like our sun, in the vicinity of a black hole. This is what happens. So the sun is being sucked in to its binary partner, this black hole, and it's emitting X-rays. This is how black holes were initially discovered astrophysically, by these X-ray emissions. The first such black hole candidate was Cygnus X1. There are many, many other such candidates today. And we see from these X-ray emissions candidate black holes in the sky. These black holes form from astrophysical processes. For example, the collapse of a very, very massive star. So the name black hole turns out to be a misnomer. Black holes aren't really black. Let me explain what I mean by that. So in general relativity, the black hole solutions we're looking at are said to have no hair. What that means is they're basically unique. Once you specify the mass of the black hole, once you specify the angular momentum, how fast it's spinning, and once you specify its electric charge, the solution is unique in general relativity in 4 dimensions. The size of the black hole is proportional to the mass. It's called the Schwarzschild radius, after Schwarzschild, who discovered these solutions to general relativity. Now, I told you that quantum mechanics and quantum field theory, electrons, for example, can annihilate and form a photon. It turns out that the vacuum in a quantum field theory is dynamical. So the vacuum can pair-create particles. This is allowed by the uncertainty principle. You're basically borrowing energy from the vacuum in order to create these particles. Suppose you've got this pair creation process is happening all the time, everywhere. But suppose it happens near the vicinity of the black hole horizon. And suppose that one of the pairs of particles falls into the horizon. According to Einstein, that particle can't escape again. By momentum conservation, its pair is kicked off to infinity. So this is called Hawking radiation, this pair creation process and the particles being kicked off to infinity. So by mass conservation, it looks like the black hole is shedding particles. The black hole is losing mass. The area of the black hole horizon is just a function of the mass, the charge, and the angular momentum, because these quantities specify the solution to general relativity uniquely. Okay, so eventually the black hole loses all its mass and it evaporates. At infinity, we collect these Hawking particles, this thermal black body radiation, and find that it has a characteristic temperature. This temperature is determined by the surface gravity of the black hole at the event horizon, And we can characterize this temperature by the mass, basically. Surface gravity is inversely proportional to the mass of the black hole, and therefore the temperature is inversely proportional to the mass of the black hole. So, because black holes have a temperature, they obey the laws of thermodynamics. So what does thermodynamics say? So there's a zeroth law of thermodynamics. The zeroth law of thermodynamics just says that at equilibrium, the temperature is the same everywhere. So for example, if the room was in equilibrium, if you sample the room over here, you sample the room over there, you get the exact same temperature with your thermometer. Now, the black hole event horizon, it turns out, has an everywhere constant surface gravity. The speed at which things fall is the same everywhere on the event horizon of the black hole. Now, on the Earth, if you drop something, it falls at about 9.8 meters per second squared. But depending upon the longitude and latitude, that number slightly changes. This is because the Earth is spinning. There's an equatorial bulge on the Earth. Because of this equatorial bulge, the Earth is not a perfect sphere. As a result, the speed at which things fall slightly changes depending upon where you are. That's not true for a black hole. Anywhere on the surface gravity, on the event horizon of the black hole, the surface gravity is the exact same. In addition to the zeroth law, there's the first law. The first law is basically a statement of the conservation of energy. E equals mc squared. If you change the mass of the black hole slightly, you're changing as well the area of the black hole horizon, you're changing the angular momentum, you're changing the electric charge in a specified way. So that's the conservation of energy. The second law of thermodynamics would be the most fundamental fact in all of science. The second law of thermodynamics basically says that things fall apart. There's a quantity called entropy, which measures the degree of randomness or disorder in a system. This quantity, entropy, is always increasing in any physical process. Even though the laws of physics are microscopically reversible, we don't see, for example, a broken coffee mug spontaneously reassemble. That's because the unbroken coffee mug has less entropy than the broken coffee mug. Similarly, in physical processes, the area of the black hole horizon increases. So if you throw something into a black hole, the area of the black hole gets bigger. So this quantity, the area, is always increasing in any physical process. So Bekenstein and Hawking, so the SBH here, the BH stands for black hole, but also stands for Bekenstein and Hawking, the guys who developed this notion of black hole thermodynamics. And they identified the area with the entropy. So the entropy in a thermodynamic system is the same thing as the area of a black hole. In any physical process, the entropy of the universe, which is to say the sum of the areas of all the black holes in the universe plus the entropy of everything else, is a non-decreasing function. So the laws of thermodynamics, some of the basically tell us how things behave when you have large numbers of degrees of freedom, match the behavior of black holes. So what's thermodynamics? Let's consider a gas in a room. So in a gas in a room, if you take 22.4 liters of gas, that contains Avogadro's number of molecules. That's 6.02 times 10 to the 23rd molecules. Now, we can't keep track of the positions of 6.02 times 10 to the 23rd molecules and their velocities. Fortunately, we don't need to. All we're really interested in are quantities like temperature and pressure. So there are lots of different configurations of gas molecules consistent with the measurement of temperature and pressure. The number of configurations of the gas molecules is the number of quantum states of the system. The logarithm of that is the entropy. So entropy basically counts the number of configurations of the gas molecules in the room, for example. It's a measure of our ignorance of the true quantum state of the system. So in this case, there's an underlying theory of statistical physics that explains thermodynamics. There's an atomic theory. We know they're atoms. We know the atoms are positioned in various places and moving with various velocities. That set of information is what's necessary to define a particular quantum state. The fact that we don't know what the quantum state is captured by the entropy. Now, since black holes have entropy, a very natural question to ask is, what is the entropy counting? What are the quantum states of a black hole? As I said, if you specify the mass, the angular momentum, the electric charge, you specify the geometry exactly according to Einstein, there should be no entropy. But the fact is, there is an entropy. So what are the underlying atoms of space-time that give us a statistical description of the physics of black holes? So that's what we're after here. So, in order to answer this question, a major clue is supplied by the fact that black hole's entropy grows with the area of the event horizon. It does not grow with the volume. So if you take a gas of molecules in a room, and you make the room bigger, the entropy will scale with the volume. That's not what's happening for a black hole. Unlike the gas, we can specify the exact quantum state of the system with one dimension less worth of information than we thought. It doesn't scale like a volume, it scales like an area. This is surprising, and this leads to a general principle in gravity called the principle of holography. This principle basically states that the number of degrees of freedom of a gravitational system is one less in dimension than what you would naively expect. This particular principle is realized in a particular model of quantum gravity called string theory. So, what's string theory? We saw that gravity as a quantum field theory failed. Gravity as a quantum field theory failed because when you sum all these Feynman diagrams for masses exchanging these gravitons, that sum is infinite. Now, suppose we were to, instead of thinking about these as point particles exchanging a point-like force carrier, suppose we were to smear out the interaction. You think about the particles as being little loops of string. You think about the force carrier as also being a little loop of string. If you do this, it turns out that these diagrams in string theory, when you sum them up, they're finite. So we can make sense of gravity by, instead of thinking about point masses, by thinking about loops of string. Now, we have to pay a price. Nothing comes for free. The price we pay is that string theory is not a four-dimensional theory. String theory lives in higher dimensions. So a natural question to ask may be, what happened to the higher dimensions? Why do we only see four dimensions in nature? And we'll return to that at the very end of the talk. In fact, in order to prove the consistency of string theory, the mathematical consistency of string theory, and figure out how many dimensions it lives in, we need to use some very cool mathematical tricks. One of the mathematical tricks we use is the sum of the integers, 1 plus 2 plus 3 plus 4 plus 5, etc., in a particularly well-defined sense that limits to minus 1/12. We use this fact in order to show the string theory is consistent in 10 space-time dimensions. So it's a very, very strange mathematical fact. It's bizarre, but it's true. In a particular sense, the limit of the sum of the integers is minus 1/12. Now, if you look at the equations of string theory, the equations of the string give general relativity. The lowest energy excitation of the closed string is the graviton that we saw previously. So the particles we see in gravity arise from string theory. Moreover, if you think about exciting the string in different ways, you can imagine these other excitations being other particles that we see in nature. In fact, string theory is really a web of interconnected theories. There are 5 string theories that live in 10 dimensions, and they're related to an 11-dimensional theory called M theory. And we can consider these theories, this M theory in various limits gives these different string theories. And based on this stringy physics, we can recover semi-realistic models of particle physics. We can also recover the basic idea of cosmological inflation, the early exponential expansion of the universe shortly after the Big Bang has models in the string theoretic framework. So string theory is very good in that it captures the salient features of quantum field theory. It also captures gravitation. And as I'll show you, it obeys this principle of holography, at least in certain contexts. So, I claim the world is a hologram. What I mean is, there's a particular solution of what's called type 2b string theory in 10 dimensions. The solution is called anti-de Sitter 5 cross S5. Anti-de Sitter space is a maximally symmetric solution to the Einstein equations with negative curvature. A very simple example of this anti-de Sitter space is this tessellation by Escher. If you think about the places where the fish heads meet, and you think about all those places being equidistant, you get what's called the hyperbolic plane. This is two-dimensional anti-de Sitter space. The solution to string theory I'm thinking about is a 5-dimensional version of this two-dimensional anti-de Sitter space. So you take string theory on this weird background, AdS5 plus S5. This theory is exactly the same, identical to a quantum field theory which lives on the boundary of the space. The boundary of the space is 1 dimension less than the dimensionality of the space. So if you take a disk, for example, a solid disk, the boundary of the disk is just a circle. The circle is one-dimensional, the disk is two-dimensional. Similarly, if you take a solid ball, the boundary of the solid ball is a sphere. The solid ball is three-dimensional, the sphere is two-dimensional. So if you look at anti-de Sitter space, this five-dimensional anti-de Sitter space, the boundary of this anti-de Sitter space is four-dimensional. A quantum field theory called n equals 4 super Yang-Mills, which lives on this four-dimensional space, it turns out is exactly equivalent to string theory on this anti-de Sitter space, which is five-dimensional. So the moral here is you shouldn't think outside the box, you should think on the surface of the box, because the physics on the surface of the box is exactly identical to the physics inside the box. The two are the exact same. We say the two are dual. So in this sense, in this anti-de Sitter space, we can have black holes living in anti-de Sitter space, and the gravitational physics of these black holes in anti-de Sitter space is exactly the same as the physics of the quantum field theory, which lives in the boundary of the anti-de Sitter space. So that's one a remarkable fact. The world is in fact a hologram in this precise sense. The other remarkable fact is the number of dimensions that we see in space-time is a matter of perspective. We can view the physics in terms of gravitational physics in 10 dimensions. We can equally view the physics in terms of non-gravitational physics, this quantum field theory, which lives in 4 dimensions. This 4-dimensional theory and this 10-dimensional theory have exactly the same physics. That's amazing. Moreover, this dictionary that relates physics in this anti-de Sitter space with this quantum field theory, this conformal field theory, which lives in lower dimensions, is what's called a strong coupling, weak coupling duality. What this means is that very complicated expressions on one side are very simple expressions on the other side. So you can think about a dictionary. This dictionary, it's a dictionary that relates two different languages. In one language, extremely complicated expressions become very simple expressions in the other language, and vice versa. Very simple expressions become very complicated expressions. So using this dictionary, we can study gravity without gravity. So we're going to consider gravitational systems, black holes, in anti-de Sitter space, and then analyze them in terms of quantum field theory. Now, when I say easy, maybe I should be saying easier. These calculations that I'm saying that are easy are significantly easier on one side than the other, but they may be too difficult for me to do. It could be that a lot of interesting physics is just intractable because you don't know how to do the calculations, even if they are in principle easier. Okay, so let me think about anti-de Sitter 5. Let me think about a black hole which lives in anti-de Sitter 5. This black hole has a mass. The mass of the black hole scales like some parameter n squared. Okay? The entropy, the area of the black hole, also scales like n squared, it turns out. So I told you there was this dictionary. We can go from this gravitational theory, the string theory in anti-de Sitter 5, to a quantum field theory which lives in 4 dimensions. So how do I translate the mass of a black hole to something in quantum field theory? Well, quantum field theory, I told you to specify this thing, had to tell you about the fields, had to tell you about how they interact. So when I do this, let me construct all the words I can in terms of my quantum fields that have a length n squared. The number of, how many such words are there? The number of such words should tell me something about the entropy of the black hole. In this n equals 4 super Yang-Mills gauge theory, if I tabulate the number of words that have a length n squared, and I account for things like group theory, and I account for things like equations of motion, I'm careful, I find the number of such words is e to the n squared. The logarithm of e to the n squared recovers the entropy of the black hole. So this is a model then for understanding what the microstates, what the quantum states are that you associate to certain black holes in string theory. So what do these black holes look like in terms of quantum field theory? In a very simple example, suppose I've got an alphabet with only 3 letters, X, Y, and Z. These are 2 different words of the same length in this alphabet. And we see that if we consider all the possible words of a given length, we can generate an entropy. Now, we also see that typical words are basically random strings constructed out of X's, Y's, and Z's. As a result, they're very hard to distinguish from each other. this is going to be very important when we try to characterize these black holes in terms of gravity again. So because these words look like random strings, the distribution of x's, y's, and z's are the same. The separation of x's, y's, and z's are in general the same. They follow the same statistical distributions. So in very, very special examples, the most symmetric examples you can construct, in these very special symmetric examples, you can take each of these words and translate them back into a geometry. So the classical black hole, there's a horizon. Deep inside the horizon is a singularity. And near the horizon, it turns out the geometry looks like one of these anti-de Sitter spaces. Very far away, at asymptotic infinity, you've got flat space. Now, if you look at what happens when you translate one of these long words into a geometry, you get the same sort of picture. Very, very far away, it looks like flat space. As you go in, it looks like an anti-de Sitter space. And these individual solutions, however, don't have horizons, they don't have singularities. They start differing from each other at the scale where the horizon would have been. So suppose you then average over all the possible caps that you can have in this geometry. Each cap corresponds to a particular word of a particular length in the field theory. When you do this averaging, you recover the classical picture. You recover the solution from general relativity. So the geometries which are intrinsically stringy, which are fluctuating beyond the horizon, where the horizon would have been, are the origin of entropy. And the fact we don't know which cap we're looking at is the thing which we call entropy for the black hole classically. Now, for the most symmetric examples, this is true. For less symmetric examples, we don't know if this is true. And this is one area of active investigation in my community right now. Trying to understand what these microstates, these quantum states you associate to a black hole are in these less symmetric situations. So what is this averaging I'm doing? So pointillism was a 19th century movement in art in which you applied pure color to a canvas. If you step back and look at the painting, you see that it requires tonality, it requires definition, it requires texture. The structure in the painting is emergent, in other words. It's a consequence of your eye doing certain averaging. The computer screen, the projector, they all operate on similar principles. That's, in a sense, what averaging is. So suppose I look at an arrangement of black squares and white squares. The number of black squares and white squares are related to the mass of my black hole solution. And I can arrange these black squares and white squares in many, many different ways. Here's another arrangement of the blacks and whites. Here's one more arrangement of the blacks and whites. If I average, I find that I get gray, irrespective of how I arrange these black squares and white squares. So that's basically what's happening. I've got structure at the quantum scale, but I'm averaging. When I average over this structure, I recover a new scale. This is the scale of the classical horizon in general relativity. So this is a model for the origin of gravitational thermodynamics. This is an idea that many, many people contributed to this development. Samir Mathur is probably the greatest proponent of this in my community. And the work I told you about these long operators, these long descriptions of words in quantum field theory describe black holes, is stuff that I did with my collaborators about a decade ago. So I try to write a couple papers on this every year to try to push what we understand about this. We're trying to see whether we can understand gravitational thermodynamics in less symmetric settings using this language. Okay, so we're also here today for jazz. And the New Yorker's jazz critic, Whitney Balliet, once defined jazz as a sound of surprise. So in my community, we heard the sound of surprise maybe a month ago. So in June 1916, Einstein predicted the existence of gravity waves. These gravity waves are basically ripples in the fabric of space-time. We saw gravity waves, or the LIGO experiment saw gravity waves, I should say, in September 2015, announced the results in February this year. So a little less than 100 years after Einstein predicted this, we saw this. So what happened? There's a black hole with 29 solar masses. There's another black hole with 35 solar masses, 36 solar masses. They collided, and they merged into a new black hole with 62 solar masses. 3 solar masses of energy were radiated away. They radiated away in terms of gravity waves. Now, it turns out that this event happened 1.3 billion years ago. It happened very far away. And we finally heard this happen now. It turns out you can actually listen to the gravity waves in the acoustic wavelengths. This is what they sound like. It's pretty amazing that you're listening to a black hole merger that happened 1.3 billion years ago. Now, this black hole merger, the power generated by the merging of the black holes is about 10 to 50 times more than the power radiated by the rest of the observable universe when this happens. So it's a very dynamical event. We expect that LIGO will see such things once every few months, and they were fortunate to see one such event already. So these black holes that are emerging are astrophysical black holes. They're not the black holes in anti-zero space I'm talking about, but they're spinning black holes. It turns out these spinning black holes can also be described by this conformal field theory. Now, we know many things about black holes, and many things we don't know about black holes as well. So Andrew Hamilton at the University of Colorado very generously let me show these simulations for what happens when you fall into a black hole. You're seeing the light curving around the black hole. In fact, if you don't have a pair of mirrors, the best way to see the back of your head is to approach a black hole, because light will go around the black hole, and you can see your back from the light that goes around. As you're falling into the black hole, you're seeing that the amount of the universe that you can observe is becoming narrower and narrower and narrower. Eventually, you'll fall into the black hole, never to escape again. So this is basically what you see. Now, black holes are dangerous places. Any self-respecting starship captain has a heads-up display. So this is a black hole. There's a time, which is measured on the right-hand side. If you consider Sagittarius A star, which is the black hole at the center of our Milky Way, if you're falling into the center of our Milky Way, that time there is measured in seconds. Now, the green, the yellow, and the red zone, the orange and red zones, basically describe certain regions around the black hole. The green zone has stable circular orbits. As you enter the yellow zone, the circular orbits are no longer stable. And that's what we're entering right now. And then we will enter the orange zone, where there are no stable orbits at all, in which case there are no unstable or stable circular orbits. So in order to be in the orange zone, you need to be firing your thrusters constantly. And then you're slowly approaching the red, which is the horizon. Once you cross the horizon, you can't escape. The horizon bifurcates when you cross it, and roughly 0.1 seconds before you hit the singularity, you're ripped apart by tidal forces. The force on your legs is different from the force on your head, and this is more than anything can tolerate, basically. Everything is ripped apart. So that's what happens, in a sense, classically, when you fall into a black hole. Now, quantum mechanically, in quantum gravity, there's some evidence that because of these things like these microstates diverging from each other at the horizon scale, it may be you experience quantum gravity effects near the horizon. We don't know if this is what happens, but this is another area of active investigation to better understand black hole physics. So there are a lot of challenges for the second 100 years of general relativity. We hope that what you learn about black holes, the singularities that live in the black holes, for example, also translates to more general settings, like the Big Bang, for example, the initial singularity whence the universe began. We also understand, in some sense, through this principle of holography, how anti-de Sitter solutions to string theory have their true gravitational degrees of freedom captured by this conformal field theory, this quantum field theory, which lives on the boundary. What happens when we're living in some other space? We're not living in a space with a maximal negative curvature. It looks like we're living in a space with a positive curvature, called de Sitter space. So how do we understand the gravitational degrees of freedom of de Sitter space in terms of things like the principle of holography? That's another area that we would like to better explore. We've noticed that in very simple contexts, the simplest black holes in anti-de Sitter space, space-time is emergent, and that we can see how metrics, how geometries in Einstein's theory arise from averaging over microscopic structures in quantum field theory. Can we generalize these lessons, especially in settings which are more reasonable in their cosmologies and more similar to our universe? Finally, we experience 4 dimensions. There's up and down, there's left and right, there's forward and backward, and there's time. Why is this? Why is it that the universe is four-dimensional when string theory says there are higher dimensions? What happened to the higher dimensions? How do we, maybe they're very, very tiny. And in fact, certain models, the shape and the size of these extra dimensions is what determines particle physics in our universe. So we'd like to better understand how space-time, how these dimensions of space-time are organized. And in fact, since dimensionality in space-time seems to be not something fundamental, it's a matter of perspective, we'd like to better understand what the true degrees of freedom of the universe are. And this brings us back to the very simple questions I mentioned at the beginning of the talk. What is the fundamental composition of space, of time? Where does matter come from? Why does the world look the way it is? How did the universe begin? And these are challenges for us to address in the second 100 years of Einstein's theory. We'd like to understand, finally, what quantum gravity really is. And we don't have a good answer to that either. So thank you very much.